So on general grounds, based just on symmetry and assumptions what are dynamical degrees of freedom, we have proposed an action for the gravitational theory. Now we're going to use this action and minimal least action principle to derive equations of motion that follow from this action. So to do that, we have to vary the proposed action, Einstein-Hilbert action, with respect to the metric. So we have to vary the following quantity. 1/16 pi kappa delta G and d4x square root of G mu nu R mu nu plus lambda plus delta G of Sm matter. So this is just R, and this is variation of this quantity. Now this is equal to minus 1/16 pi kappa integral over d4x, and here variation of the square root of the determinant metric multiplied by R plus lambda. Well, this is just this. So this is variation of the first. Now we're going to write variation of this. And a variation, you'll see. Square root of G multiplied by delta G mu nu times R mu nu. So this is variation of this. Plus square root of modulus of G delta R mu nu multiplied by G mu nu, and the remaining thing delta G of Sm. So now we want to find separately each contribution like this, one after the other. So the bracket is closed here, after the other. Let us do first this. To do this, let us do the following. Let us do the variation of the log of the determinant of an arbitrary matrix M. So in this chain of relations that I'm going to write now, we will keep track only of linear terms with respect to the variation of M. Only linear term with respect to this. So this variation is just log determinant of M plus delta M minus log determinant of M. Well, before I move further, I just realized. So what we do, of course, when I wrote this, and I assume that everybody knows how to vary field action with respect to the corresponding field. But let me just say a few words. So what do? We consider this action, and we want to slightly deviate the metric. So we add to the metric small deviation. And then the variation of the action, of this full action and Einstein-Hilbert action, is just the difference of S plus G plus delta G minus S of G. And if we are in the vicinity of the critical point of such a metric that minimizes the action, this variation is equal to 0. That's what we do. So now, coming back to what we have been doing, I am looking for the variation of this, but I do a more generic thing. I vary log of the determinant of an arbitrary matrix M. So this is just by definition is this thing. And let me do the following. So this is log of the determinant of m plus delta m divided by the determinant of m. Well, this is just a property of the log. So this is equal to log. Ratio of the determinants is the determinant of the ratio of the matrices due to the property of the determinant. So this is just then m minus first m plus delta m. And then I open up the brackets. So this is log determinant 1, so unit matrix, plus m to the minus first power times m, like this. And then by the property of the determinant is such that log determinant is nothing but the trace log. So this is then trace log of the same quantity, delta m. And at the very last step, we're just going to keep only linear in delta m term. So to linear order, this quantity is as follows. This is just approximately to linear order, trace times, nothing like that here, m minus first delta m. So let us apply this expression to the variation of the log of the square root of g. Well, this is just variation of the log of the square root of the determinant of g mu nu. Well, by definition. But this is minus 1/2 variation of the log of the determinant sorry, this is modulus of the determinant of the inverse metric g mu nu with upper indices. Well, applying this formula, this is nothing but minus 1/2 g mu nu delta g mu nu. So, as a result, as follows from these formulas, we can find that, well, what is this? This is nothing but a variation of the square root of the modulus of g divided square root of modulus of g. So from this expression, we can find this variation. So we have found the variation of this guy, that the square root of variation of the square root of g is minus 1/2 of square root of g times g mu nu delta g mu nu. This term is obvious. It is already proportional to delta g mu nu, like this one. And now we continue with this term. So, to find this term, let us fix local Minkowskian reference system, where g mu nu is approximately eta mu nu around the point, a point x, and gamma mu alpha nu is 0, approximately around the same point. Then, in the vicinity of this point, in this reference frame, we have that delta r mu nu is equal to delta variation of gamma alpha mu nu comma alpha minus gamma alpha alpha mu comma nu. So this is equal to d alpha, well, by definition, delta gamma alpha mu nu minus d nu delta applied to delta gamma mu alpha alpha. And in the locally Minkowskian reference frame, this is equal to d alpha, covariant derivative of delta gamma alpha mu nu, minus d nu delta gamma alpha mu alpha. And now one can see that this quantity has tensor properties. It is a tensor, despite the fact that these two guys are not tensors. This is tensor because the non-tensorial part cancels between these two contributions. So we have a relation between this tensorial quantity and this tensorial quantity. Although this relation was obtained in this locally Minkowskian reference frame, because these are tensorial quantities and transform multiplicatively. So if this relation is valid in this reference frame, it is valid anywhere else. So this relation is true in any reference frame. From this relation, we have that G mu nu times delta R mu nu, which is exactly the variation of delta R. Oh, sorry, no, this is not true. So this quantity stands here. So this quantity is equal to d mu applied to G alpha beta delta gamma mu alpha beta minus G alpha mu times delta gamma beta alpha beta. So this is nothing but a covariant derivative of some quantity which we can call delta u mu. This quantity we call delta u mu. Now we're going to use this expression in here under the integral. So just to stress again where we are in our derivation. So we are looking for the first variation of the Einstein-Hilbert action and want to put it to be 0. So the first variation of the Einstein-Hilbert action is, as we have been observing already, is 16 pi kappa integral over d4x variation of the square root of g times r plus lambda plus square root of modulus of g delta g mu nu times r mu nu plus square root of modulus of g times delta r mu nu times g mu nu plus variation of matter action. So far we have found that this guy is the following. It is minus 1/2 square root of g times g mu nu times delta g mu nu. So it is proportional to this quantity. This term is already proportional to this quantity and has appropriate form for further study. Now we have been studying this guy, and this guy we found to be g mu nu times delta r mu nu is equal to d mu of g alpha beta delta gamma alpha beta mu minus g alpha mu delta gamma beta alpha beta. And this we denoted as d mu times delta u mu. So this variation is the total derivative, as can be observed from this formula. So under the integral over the space-time manifold, this quantity, so this variation is equal to d for x square root of modulus of g d mu to the total derivative delta u mu. And because it's a derivative of integral over the total derivative, one can apply Stokes theorem or Ostrogradsky-Gauss theorem in this case in curved space-time, and then this is the integral over the boundary of our space-time manifold d sigma mu times delta u mu. Well, this is where d sigma mu can be written, this is a vectorial quantity, which is a vector at, whose modulus is proportional to the area or volume of the three-dimensional boundary of the four-dimensional space-time manifold, and the vector is directed along the normal to this element. So it can be written like this. It's n mu, normal vector, square root of the determinant of the three-dimensional induced metric on the boundary, induced from the metric g mu in space-time, times the parameterization of the boundary of space-time. So then the study of these boundary terms is a very interesting and separate subject, but at this point we consider, in this course, we consider the variation, such variations that at the boundary the variation is zero. As a result, this term doesn't contribute. So this term is just zero after the integration by parts. It doesn't contribute to the equations of motion. But the consideration of boundary terms is a separate, interesting subject, which is not covered in our course here. So, as a result, combining all these things together, so I assume that this is zero at the boundary of the manifold. So, as a result, combining this variation, this and this, we obtain that one has to put to zero the following quantity: variation of the matter action minus 1/16 pi kappa integral over d4x square root of modulus of g times r mu nu minus 1/2 g mu nu times r minus 1/2 g mu nu times lambda and multiplied by delta g mu nu. So, to complete our exercise, what we need to find is this variation.